Right, hello everyone, welcome to the latest WatchPoint episode. Now we're going to look at something a little bit different. We've looked at just GDB before, now we're going to look at other debug tools. And we're going to look at two of the most commonly used, Valgrind and AddressSanitizer. Kind of similar, but a bit different. We'll look at this just an early just view on how easy actually they are to use. First time I tried to use both, I admit I was a little bit intimidated. Thought these sound really cool, but surely they must be complex if it's doing such magic. And actually both are wonderfully simple and easy to use. So we're going to look at specific instances. So Valgrind, often mispronounced Valgrind. I assumed it was some kind of portmanteau of value grinder, but no, it's Valgrind. It's some kind of Norse god or something. And in fact, it's a suite of tools, but the most commonly used and the default tool is Memcheck. So we're going to look at that one first of all. So here I have a trivial program which contains a buffer overrun. Obviously not hard to spot that one, but we've all been there. We've all done similar kind of mistakes, all too easy in C, and the results can be really subtle. You might not notice for a very long time. Actually, let's just show you something. If I just compile this as normal and run it, then yeah, like there's no kind of harm done, right? I don't notice, and in fact this program we can deduce that it isn't going to do anything wrong. But clearly if I had a more complex program and I've done that, who knows what I'm writing into, some other object, and I may well not notice for some time later in some really horrible to diagnose way. Wouldn't it be good if the system could tell me that? Well, let's run it through Valgrind and I'll have a little bit of a think. There we go. Well, I told you it couldn't be simpler, right? Now, you didn't notice that took a long time. Actually, that took a little bit longer than it usually does, but it does run pretty slowly, actually. Valgrind will often slow down, one, maybe two orders of magnitude. So you're not going to run it in production. But if you've got a memory problem that you're looking for, it can be very useful. So let's just look at what it's telling me here. Well, it's telling me exactly what the problem was, right? So it says that there was an invalid write of size 1, buffer.c line 7. And sure enough, here's line 7, and there it is. So how useful is that, right? So that's one way. So it does run very slowly, but it couldn't be easier and simpler to use. And in many cases, that slowdown is nothing compared to the amount of time you'll spend bashing your head against the wall. But maybe I want to run a little bit quicker, and I can do that with AddressSanitizer. So AddressSanitizer, again, like Valgrind, is a suite of tools. The sanitizers are a suite of tools. But unlike Valgrind, we change the compiler. The compiler will generate special code to look for these kinds of problems. So if I go GCC, it was originally in Clang, but it's been ported into GCC for some time now. So sanitize, and I can tab complete that, right? So AddressSanitizer is the most common. By the way, look, if I tab complete here, you can see there's a whole bunch of them. So you can kind of guess a lot of these what they are from the name, and we can have undefined behavior. We can look for thread sanitizer, but we're going to keep it simple in this example and just look at AddressSanitizer -G again, so we get line information. And now I run my program, and here we are. Look, it tells me there's a problem. It tells me there's a little bit more information, perhaps you could say, a little bit more readable. But anyway, heap buffer overflow at buffer.c line 7. Right, very, very useful. It will run, as I say, quicker. Still there's some slowdown, and it does consume quite a lot of memory, but we're talking, perhaps it'll run at half speed rather than like an order of magnitude slower. And of course it does, though, require that I recompile my program, but in a very simple way. Clang works exactly the same. As I say, originally a Clang project. So there we go, and you'll see if I do that. Looks mighty similar. So that's it. Very simple for AddressSanitizer and Valgrind. Let's just look at a little bit more though. Talk about how they work. So what Valgrind is doing, so it's working on the object code, on the binary, and it's doing a just-in-time binary translation. That is, as the program executes, it's not really executing the machine code that we generated. It's actually executing inside Valgrind, and it's like almost emulating it. Except what it's doing is one basic block at a time. It translates it into something that is functionally equivalent, but adds the kind of hooks for Valgrind. So this is very useful because it works in unmodified binaries. Maybe I don't even have the source code to hand, right? And that could be a real thing. Maybe I'm trying to find point the finger in some segv of some application and I don't have the source available. But it does, otherwise it's running more slowly. It means there's sort of certain things that it can't really do. So I'm going to show a different, that was a heap overrun. Let's look if we do it on the stack. Well, actually what we'll see here, I'm going to show a couple of things. There's some built-in stuff into the compiler these days. So if I go like that, gcc-g, but now if I'm just running this normal, no Valgrind, no AddressSanitizer, okay, that's happy because I didn't actually. Oh, okay, so I do that. So run this as normal now, and it still tells me there's stack smashing, right? So the compiler by default will put these little red zones on the stack and the return information, and if it detects that the function has smashed the stack, it can tell me and terminate like this. Very useful. It's kind of a security feature, right? Because that's a very common kind of security attack, is to cause those buffer overruns to cause the return from the stack to jump into the code you just wrote onto the buffer. So this will catch that and prevent it. Very useful. But it kind of gets in the way of the demo that I want to show here. So I'm going to turn that off, because obviously if I were in a more complex program, it might not notice. Like I might overwrite other like local data on that stack or something. So let's turn that off. fno stack protector and run. And yeah, runs fine. Let's run it in Valgrind. And no errors. No errors detected. It does tell me that there's some heap in use at exit, because I've got a leak there, so it tells me about that memory leak, but I didn't see. This is why I need to do -g, because I didn't give you the line information. So give that again and run that in Valgrind. Now it's got debug info, and it can tell me a little bit more. No, it doesn't in that case. Okay, I thought it was going to tell me. Okay, it does tell me run with leak check equals full to see details of the leaked memory. So -- leak check equals full. And that's a bit more useful. Okay, so it's telling me that there was this block allocated at buffer.c line 6, and I never freed it. But it's not detected that stack buffer overrun here, right? That it seems to think is fine. Let's run that now with the AddressSanitizer equals address -g buffer.c. Now I run that, and that does spot it. Okay, because the AddressSanitizer is done in the compiler. It's magic done by the compiler, and the compiler knows, right? The compiler knows about that object that's allocated on the stack and what its bounds are. Valgrind doesn't know, right? It has no way to know because it doesn't have access to the source code. Well, maybe you could say it could try and figure it out from the debug information, but that's not how Valgrind is meant to work. So, very quick overview, but you can see hopefully there how easy both of these tools are to use. We'll look at some of the other features and some of the other tools in a subsequent episode. But for now, thank you for listening. Goodbye.